All right, so the focus of this lesson is to start looking at ways of finding derivatives without using a GDC rather quickly. And the focus, as you can see from the title, is power functions, which, if you're not yet aware, are actually really quite pleasant to work with if you want to find the derivative. And so let's just look right here. In general, I have a function here. It's a cubic function, which is a type of power function, 5x to the power of 3. The derivative of this I can find quite quickly by just imagining this power and multiplying it by the coefficient. So my derivative will start, oops, that's the inverse, not the derivative. The derivative will start with 5 times 3, which is 15, times x to the power of, and we just subtract 1 from the power of the power function here. So instead of to the power of 3, it's power of 2. And that's it. Now, there's a lot we can do with that. And as function, please don't think all functions are power functions, but a lot are. And, polynomial functions are a series of different power functions. And so a lot of functions can be differentiated really, really, really quickly here. Now, for something like this, we have 2 divided by x to the power of 4. If I want to differentiate this in the same way, I need to first write this as a power function. Right now, it's not written as a power function. In this case, though, I can just rewrite the function as 2 times x to the negative 4, using my understanding of negative exponents. Now it's written as a power function. Now I can differentiate it quite nicely. And so in this case, it's going to be negative 4 times 2, which is negative 8, times x to the negative 4, take away 1, which is negative 5. So negative 8 times x to the negative 5, which can also be written as negative 8 over x to the positive 5. Neither of those two was better than the other. Just keep in mind, a negative exponent means dividing by some positive exponent. And so we always want to be familiar with how to write those. So I'll tend to write them in both different ways. Here, I'm dividing 2 power functions, which if we try to just differentiate it as is, we're almost certainly going to do it incorrectly unless we've learned more that I've told you. I want to write this as a single power function, which I can do using my exponent laws. I can simplify x to the power of 2 divided by x to the power of 3 as x to the negative 1. And so now I've simplified my function to 2 times x to the negative 1. Now, similarly, I can write the derivative as 2 times negative 1, which is negative 2 times x to the negative 2. Always subtract 1 from there. So notice I've differentiated 3 different functions really quickly. For this, we actually have a linear function, which we can imagine as being negative 1/2 x to the power of 1. And it's not wrong to think about it that way. And then we'd go 1 times negative 1/2, which is negative 1/2. And then we'd have times x to the power of 0. Well, anything to the power of 0 is 1, so we end up with negative 1/2 times 1, so just negative 1/2. And even better going forwards is that this is a linear function, and so remember, for any linear function, the coefficient of x is the gradient or the slope. And in that case, that's what we're finding. The derivative is the gradient of the function at any given point, and a linear function has a constant gradient. That said, here, almost the same thing, but now I have an x in the denominator, and so if I use my understanding of negative exponents, I can write this as negative 1/2 times x to the negative 1. Again, if it's possible to write something as a power function, we can differentiate it quite quickly. Although as it was written at first, that is not a power function how it's written. And now I can just go negative 1/2 times negative 1, which is positive 1/2 times x to the negative 2. I could leave it like that, or I could write it as 1 over 2 times x squared. I'll leave both those for my derivative. All right here, I have f of x equals negative 1/2. It's a constant, which, again, it's not wrong to think of this as x to the power of 0. And then if you did that, you would go 0 times negative 1/2 is 0. But really, it's a waste of time because this derivative is just going to be 0, because a function of negative 1/2 is just a horizontal line. A horizontal line is the slope of 0. So however you look at it, this is a nice, pleasant derivative. And it's always useful to remember the derivative of a constant function is always going to be 0, because a constant function is just a horizontal line at some value. Final row, I got a pretty straightforward polynomial function here, which we can differentiate quite nicely. So 2 times 4 is 8, so I have 8x cubed, negative 6x. That's just the derivative is just negative 6. Remember, that's a linear function, negative 6 being the slope. And then I have plus 4, that's a constant. The derivative of a constant is 0. So while it's not wrong to put a plus 0, it's clearly not necessary. There's my derivative. So next, I have something very similar. It's the same function as before, but everything's being divided by 2. And so what I want to do is before I differentiate anything, I'm going to write this without that denominator, which is quite pleasant because everything here in my numerator is an even number anyways. So divide everything by 2, I get just x to the power of 4 minus 3x plus 2. So that's f of x, not my derivative. So now I can differentiate this using the power rule a few times. So I have 4x cubed minus 3x, and that's it. And so lastly, I have that same polynomial now being divided by 2x. So same idea, I want to take everything up here and divide by 2x, which means, keeping this as f of x for a moment, 2x to the power of 4 divided by 2x is x cubed. Minus 6x divided by 2x is just minus 3. And 4 divided by 2x, I can write that as just 2 times x to the negative 1, or 2 over x. The reason I'm writing it as 2 times x to the negative 1 is, as we've seen, writing fractions or denominators with a negative exponent is quite pleasant for finding derivatives. And now the derivative of this I can find quite quickly. So I have 3x squared minus 0. So I guess I'm not going to bother writing that down. Plus 2 times negative 1, so negative 2. I'll put that back to being a negative. Negative 2 times x to the negative 2. And while that's great, I'm also, like I've done before, I'll rewrite this as well with a fraction with it. And again, neither of these two are better than the other. We should just understand that they're equivalent. All right, so for this, I have two differentiable functions, f and g, and you're given some information about the derivatives at different points. And then we're told, okay, well, what if function a is 2 times g of x minus f of x? What's the derivative at 1? Well, in this case, because all I'm doing is finding a sum or difference of functions, and I'm just multiplying them maybe by some constant, then I can just use what we've kind of done before. So, for example, a prime at 1 is going to be the same as 2 times g prime at 1 minus f prime at 1. Now, I will say, if this function a was 2 times g of x times f of x, that would change things a lot. But it's not. And so for the time being, we'll just stick with the simplicity of things. And we have 2 times g at 2 times the derivative of g at 1 is negative 2. So I have 2 times negative 2 minus f prime at 1, which we can see is 2. And so I end up with negative 6 for that. Similarly over here, I want to find b prime at 2. And so same idea. I can find b prime at 2 by finding f prime at 2 divided by 10 minus g prime at 2. All of which are told in the question again. F prime at 2, I can see, is 5, and g prime at 2 is negative 1. And so I have 5/10 minus negative 1, which is a half, plus 1, which is 3/2. All right, last question. I have g of x is this 2x squared minus 8 over x, as you can see parts of it right there. I want to first algebraically determine the equation of the line tangent to this function when x equals 2. In earlier lessons, we learned how to use our GDC to find the equation of the tangent line. In this case, though, when x equals 2, I don't know, let's say it's approximately here. I want to imagine the equation of this tangent line here. All right, that's just visualizing what we're doing. And so to do that, first I need to find a few things. I need to find the derivative at that point, as well as the y value at that point. So I'm going to maybe find the y value first. So I know what g of x is, and so if I want to find g at 2, that's the y value at that point. I just need to take my function and replace everything with 2. So I have 2 times 2 squared minus 8 over 2. And I pretty quickly get 4. So I know this point here is at 2, 4. All right, now I need the slope at that point. This is where my derivative comes into play. So I want to find g prime at 2, which again, looking at my function, I can use the power rule, especially if I first take g of x right here, and I write 8 over x as 8 times x to the negative 1. That makes it a little more helpful for me to get to the power rule right away. And so differentiating that, I can see, maybe first I'll find g prime at x before I put the 2 in. So I have 4x plus 8 times x to the negative 2, which, keep in mind, is the same as 4x plus 8 over x squared. And now if I want to find g prime at 2, because I want to find this one, x equals 2, I get 4 times 2 plus 8 over 2 squared, which ends up being just 8 plus 2, which is 10. So I now know the slope of that tangent line, what I drew in orange there, is 10. And so now I can put this together using one of the linear functions we've used before. I'll use this one, y equals mx minus x1 plus y1, the slope point or gradient point form of an equation. And so the slope at this point is 10x minus 2 plus, and the y value at that point was 4. And while I'm technically done there, if I just clean this up a little bit, I should get y equals 10x minus 16, which is a nice form to keep the equation in, although the question doesn't actually specify what form to write the tangent line in. Lastly, the gradient of g of x is negative 10 at some point. Okay, where is that? So at some point on this function has a gradient of negative 10, which means the slope is going down. So to find that, I need to take my derivative, which we've already figured out. So I'll write this down again. G prime was 4x plus 8 over x squared. But at some value of k, this equals negative 10. So I can make this just equal negative 10 as long as I just take these x's and change them to k's. So that's really what we're finding. At some point, when x is equal to k, we have this. And so now, if I'm trying to figure out where this value of k is, I just need to solve this equation here, which I can do many different ways. We could try to come up with an algebraic method. However, quite often that is more work than it needs to be. So I would personally just solve this by graphing. Graph that equation there, or 4x plus 8 over x squared. Graph that equation there and see where they intersect. Or in some other way, it's really up to you. As long as it's fairly quick, you should get k being approximately negative 2.76 to 3 significant figures, which if I look at my graph, negative 2.76 has got to be roughly here, which looks good in the fact that the gradient there definitely is negative. I don't have much detail on my graph. I can't tell just from looking at that if it's correct, but I can tell it seems to be accurate. All right, and that's it.